Our next speaker is Craig. Craig Labovitz is CTO of Nokia Deepfield business line. Prior to Deepfield becoming part of Nokia in January 2017, Craig was co-founder and CEO of Deepfield. So without any further delay, I hand over to Craig.
Great. Well, thank you. So yeah, my name is Craig Labovitz, and I'll be speaking a little bit today about how Nokia Deepfield uses ML and AI in the context of both network traffic engineering and security. But before I begin, just a little bit of an aside. While today we are very much in a golden age of ML and AI as applied to networking, it always hasn't been this way. In fact, when I first started my career, I was an AI PhD student at the University of Michigan. But the start of my career coincided, first slide please, sadly with what then or later was called the ML winter. And I don't know if the slides are advancing or if it's just a delay. We'll give it a moment.
Next slide.
There we go. So my career began actually in 1992-93, where it was clear that the great hope of ML and AI had not been met. It was a time of dashed aspirations, and more critically for me in my PhD effort, a time of reduced funding, and I was sent packing, or the funding was cut. Luckily, though, networking also began about this time. Though, click ahead, please. Though, as it became clear as I joined the NSFNet project, there was a lot of interest in building what was then a T1, a 1 megabit, later T3 network. But it was made abundantly clear to me that as I applied for NSF and DARPA funding, this was great research, but never was I to use any AI or ML terms, lest I wanted the funding to be rejected. And this remained somewhat true for the next 10, 20 years of networking. Most of the focus of networking was on building the networks, on the speeds and feeds and the hardware. Very little attention, or at least relatively little, was paid to how can we monitor the network, how can we collect data, how can we automatically learn and adjust the network. And frankly, the network suffered as a result, certainly through many of the first couple decades of the internet, with significant outage, poorly understood behaviors in routing and congestion control, and certainly in security. But next slide, please. But we started Deepfield now back around 2012, really with the idea that the networks were about to change, specifically the availability of compute. The availability of compute combined with large data sets and a growing market need for automated addressing problems of QoE, improving performance, maintaining performance, responding to performance problems in the network, as well as what was then a growing issue with denial of service attacks, large volumes of traffic launched by botnets or other types of compromised devices or networks, leading to large-scale outages, making the cover of the Wall Street Journal, Financial Times, as companies and clouds and other infrastructure went offline. So back in 2012-13, we really began exploring how could we combine large data sets with ever-improving router and hardware network elements with then what was sort of bleeding edge ML and AI techniques and apply it to networking. Next slide. So when I talk about, I think, AI and ML, at least from our perspective of how it applies to networking, I'm really talking about 4 areas. Certainly, one of the largest differences is just data. Going back about 10 years ago or so, getting any data out of the network was challenging. Networks were very good about moving traffic, and certainly fixed line networks, trying to get information about quality, queue lengths, other information, was very limited, largely limited to things like SMP and collecting data every 5 minutes or every 15 minutes. Over the last 10 years, we've seen both the industry with protocols like IPFix, gRPC, and others out of IETF become commonplace. And we've seen vendors, including, I'd like to think, Nokia being at the lead, start to leverage things like the FP4 and now the FP5 to provide rich data sets in real time at multi-terabit speeds, all in ASIC, without impacting performance. Certainly empowering a new generation of algorithms, analytics, data collection, which I'll talk about next. Next slide. So with this additional wealth of data, on the next slide, please, I'll give a moment for the slide to catch up. With this wealth of data, Deepfield really is focused on some of these other fundamental shifts in networking. For the most part of the last, 1990 to 2020, network security and even traffic engineering based on things like deep packet inspection was all very much payload-based. It was payload-based in the sense of finding the magic botnet signature or the magic hacker string within the payload. This was true of antivirus, IDS, true of many DDoS appliances. The security model for most of the last 10, 15 years was also very much an external edge, the hard security perimeter. And all of this, I think, worked for 10, 15 years. But on the next slide, the market has really changed. Some of the things that have really forced changes in the industry are, number one, encryption. The ability to actually look within a packet now to extract features, to run AI and ML, are ending, if not completely over, as most commercial traffic, as well as increasingly now the botnet and DDoS command and control traffic, are all using encrypted channels. We've also gone from an age where applications ran on individual servers and enterprise machine rooms or enterprise data centers, to now where we've got most services are leveraging many different types of compute, CDN, analytics, lots of different cloud components from many different cloud vendors. And we've also gone from the age when traffic engineering was typically something you could do once a quarter, once a month, to now we have very large systems such as Netflix or others, all using adaptive traffic, where the traffic will fill or adapt. And it is for our customers a challenge to be able to respond in the same automated way to these very large shifts in traffic volume as well as in traffic quality. Next slide, please. So when we started Deepfield, one of the core ideas was not only can we use AI and ML and apply it to the problem of networking, but that we needed to look beyond the packet, needed to look beyond the payload. So one of the things that Deepfield started doing early on, and this on the right was a graph we did for a Wired magazine edition, was we began to look at not the payload, but how are different websites, how are different video applications, how are different enterprise applications, how are different IoT devices architected? Which services do they use? In the case of Facebook, for example, which CDN, which analytics, which advertising, which hosting, which data centers, all go into sort of a building block of large-scale applications, IoT infrastructure, and so on. So as part of the data, not only are we interested in the significant additional data we can get from FP4, FP5, and other routers, but can we crawl every IP address on the internet? Can we build models of every CDN, every hosting, every IoT device, and understand how those look during normal times, how they look under pressure, how they look during security events? And that indeed was one of the core founding patents that went into Deepfield when we first started this project. Next slide, please. So I've talked about the data being of critical importance to the new golden age of networking. I've talked a little bit about the features. Largely, when you have these features available, this largely becomes a big data problem. When you have data across hundreds of terabits of traffic, billions of IPs, and you've got models that are associated with these different applications in IoT, it largely becomes a problem of understanding variance from these models. And I won't go back into my early PhD work, but largely it's about sort of constraint satisfaction in understanding variance from the different models with sort of confidence intervals for understanding how things like normal video services work, how things like Netflix or Hulu or other video and over-the-top providers look like. Next slide, please. And as I think we talked about a little bit, I think the earlier talk was interesting as well, talking about the timescales. One of the things that's really driving AI and ML adoption and automation and networking is a shift in timescales. This shift in timescales applies not only to traffic engineering, which again often was a quarterly or monthly activity, now is real time, driven by large cloud providers like Netflix and others. But it turns out that the attackers, the hackers, have all largely gone down the route of automation, where most of the commercial attack services, indeed this is just a website, you can go there, all use automation, all have APIs, all have made it very, very, very dynamic to be able to launch attacks against routers, infrastructures, 4G, 5G networks, and so on, and largely driving most of our customers to adopt automated response as well, leveraging, again, both data from the routers, from the internet, as well as ML and AI applied in real time. Next slide, please. So at the end of the day, I think the overview of sort of the Nokia Deepfield approach is, number one, leverage this huge expanse of new and rich data sets available from the network, again, including things like payload and QE and headers and all sorts of information that we can now get at line speed from FP4, FP5. We combine this information with maps we build using our own infrastructure and cloud, Nokia infrastructure, to be able to build models of every IP on the internet, V4 and V6, every service, every application, every IoT device. We combine these models in real time with real-time traffic from routers and switches in our customer networks, and we use this to drive real-time automation, both for QoE as well as for security. Next slide, please. And I won't go into great detail on this slide, but essentially, I think the important relevant points from this slide is that as data comes into the system, it is both a southbound and northbound, meaning we're ingesting real-time streaming telemetry covering terabytes or sometimes dozens of terabytes of real-time traffic per second. We're combining it with our models, and those models are then driving, on the right, real-time detection ML algorithms looking for variants from the models to be able to accurately classify things like large-scale denial of service attacks, and not just the attacks, but the actual components of the attack, so that we can also use the routers to be able to block and respond to these attacks in real time. Next slide, please. So the final step, I think, with any ML or AI approach is not only the data, the features, and the algorithms, but ground truth. It can be really hard. How do you know this traffic was really an attack? How do you know that you've successfully impacted the QoE of the traffic? And this is where we spend a lot of time with our customers. This includes things like combining our models and our decisions on traffic and applications with things like DNS. So for example, if we've classified something like iTunes video, sometimes we'll actually have the DNS record that said iTunes video. So it's all about the ability to correlate the output of our ML and AI with other data sets. And this includes both, as I said, things like DNS records that provide great visibility into the application, but also things like automated labs that run through thousands of different applications. Next slide, please. So at the end of the day, I think what matters is the results. And the results of this approach of being able to leverage the data, leverage the models we're built, is that we have been able to achieve some of the highest accuracy rates in DDoS detection in the industry, far outperforming any of the payload or earlier sort of vendor models going back over the last decade. Not only can we do it for security, but we can also do it for applications and performance. And while it is good to be able to show marked improvements using AI and ML over other hardware approaches, What's really remarkable is we're providing these gains in accuracy and performance for QoE and for security on an order of magnitude greater scale. Instead of relying on hundreds of different devices in the network, we've been able to leverage the advances in silicon, FP4 and FP5 as an example, and be able to use those much richer data feeds to both provide more accuracy and do this at terabit line speed. Next slide. And at the end of the day, this all becomes sort of a virtuous cycle, where as we are ingesting data, we are making changes to the network, we are leveraging other security and other data feeds from throughout the network, and using, again, the results of those to both improve and validate our models. Next slide. And with that, I think I just have a minute or two for a couple of questions.
Thank you so much, Greg. This is very, very insightful, and I mean, it's amazing. So I will take first questions. Anybody from the in-person audience here? Because last time I was slacking on it. So any question here? Okay, I'll go to the virtual one. The first question is, you mentioned Deepfield Cloud Genome and Deepfield Secure Genome. Can you share some insights into how these are constructed from Deepfield's cloud-based infrastructure?
Yeah, one way to think of these is like when we started Deepfield, I always thought it would be amazing to have Google-like knowledge of every IP on the internet. And so we actively do crawling. We crawl every IP address, we purchase third-party data, we leverage every bit of data we can find. For example, Google publishes some data on how they architect their services. So it really is a massive collection of both data that we collect using our own servers via crawling, much like Google, as well as the combination of that data set with many different third-party, both community-driven as well as commercial feeds, all updated, give or take, about every 5 minutes.
Thank you. Thank you, Greg. One more question I will take, and then we'll go to the next speaker. So the next question is, the faster data streams are critical for real-time AI. Is Nokia expecting to use these technologies for RAN and core PM, FM data flows?
So I can't speak specifically to the product plans for some of the other groups within Nokia. I will say things, for example, like the FP4 are not unique to Deepfield business unit, that Nokia is focused on some of these foundational building blocks, including, again, things like FP4 and FP5, of building these capabilities directly into silicon. And I think for specific product plans, I'd really have to defer to the different PLM owners of the different teams for exactly what the RAN and core plans are for the adoption of these technologies.
Thank you. Thank you very much, Greg.